Fine morning to all of you. My name is Ankit Kumar. I am a PhD student at IIT Kanpur. The name of my presentation, the title of my presentation is High Energy Neutron Emission from Palladium Deuteron Codeposited Platinum Cathode in Low Voltage Electrolysis. Before starting, I would like to thank the organizers and the scientific committee and all the attendees. And I would also like to acknowledge my collaborators, Ravi Raj Nehra, he's not here. Professor Raj Ganesh Pala, he's sitting there. Professor Pankaj Jain and KP Rajiv, who are not here. All of us are associated with the IIT Kanpur. Okay, so I'll start with the contents. So I'll start with the summary of transmutation studies in pure metal and alloys. So this was done in light water. And then I will present a short summary of photon detection experiments. We try to correlate signals of photons with transmutations, if any. And then I will move to the main topic of discussion of my PowerPoint today, that is nuclear particle emission and transmutations in heavy water electrolysis. So by heavy water, I mean D2O. And then at last, the recap and way forward. So let's start. Okay, so this basically, the picture that you see is it's a typical setup of electrolysis, and it's very complex, but just to make it simple, I have a picture here. This is a carbon anode here, and we have a metal cathode. So we choose the metal cathode, the metal cathode is the one that we want to study here, actually. So the cathode could be anything. So we, in case of pure metals, we choose nickel. And then we also have done experiments with alloys like canthal. And then we got another alloy, nickel iron. And these wires typically have a diameter of 1 mm. So anode, I already told, it's a graphite. It's a 6 mm diameter. It's visible here. And then the electrolyte, the typical electrolyte that we use is 0.5 to 1 molar potassium carbonate in S2O. The supply voltage is 20 to 30 volts, and the current is from 1 to 4 amperes. The time of electrolysis ranges from 30 minutes to 14 hours. And in order to check the transmutations, we use multiple material characterization techniques. We do EDS, we do energy and wavelength dispersive spectroscopy, and then we also do some isotopic studies using time of flight, secondary ion mass spectrometry. So I'll start with my first result. So here you can see towards your left, the figure A. I have shown a graph where on the x-axis, I have chosen 5 locations on my sample. And on the y-axis, it shows the mass percentage of that wire. It's a WDS result. And it's almost like 99.42 and 99.41, all the locations. This I got from basically Alpha ISER. And after doing 11 hours of electrolysis, we found that the mass percentage of nickel reduced, and we found new elements. The new elements are iron, copper, and magnesium. So on an average, we found 20% of copper, 3% magnesium, and 4% iron. So that was what we got with 11 hours of electrolysis in pure nickel wire. On the same sample, we did some isotopic studies. And so basically, we sent our samples to another place, IIT Bombay, and then we spotted some points, and then we tried to look for the isotopic ratios of copper and nickel. So here you can see, if we look at copper 63 and 65, the natural ratio is like 70-30, but when we looked at our samples, we found an increase in the population of copper 63, and at the same point, 65 reduced. Similarly, we looked for nickel, and in nickel, it's got a lot of isotopes. So as for example, this nickel 62 has to be 3.63, but it reduced a bit. We checked it at 3 different locations. But 64 nickel, as you can see here in the last, it increased at the 3 locations. So next is we did the similar experiment with a nickel iron alloy. And again, on the left-hand side, you can see the composition of pure sample. By pure, I mean unreacted sample before the reaction. And after the reaction, again, we found 1.8% copper, 5.9% magnesium within an hour of electrolysis. So I'll quickly summarize the learnings of our light water experiments. So EDS, WES, and TOF sims confirmed transmutations. We used graphite anode, and this actually restricted anode-driven contaminations. The main finding in this work was that we found copper as the heaviest element, which was produced on the cathode, and magnesium was the lightest element that was produced on the cathode. A previous work from our group, where platinum anode was used, they found lead as the heaviest product in the cathode. So this is the paper. He's my thesis supervisor. And so we did some isotopic measurements, and we found isotopic shifts. A very good logic why these foreign elements that have been observed on the cathode could not be impurity is that even like if it would have been an impurity, the impurity would have shifted the ratios towards their natural values. Okay. So another exciting thing I discussed about 62 nickel. It has the highest binding energy per nucleon, and still it got depleted while there was a buildup of nickel 64. And the last thing is that the alloys needs less time for generating transmutations as compared to the pure metals like nickel, as I showed earlier. We found transmutations within an hour. So, and then a natural question arises: if we are seeing transmutations, shouldn't we see nuclear products, byproducts, be it particle or photons? So in search of the answer to this question, we decided to look for photons in our setup and try to correlate it with transmutations, if any. So this we have already seen. We choose either an alloy or a pure metal, and then we do the electrolysis. And then we try to look for gamma photons. So let's have a look at the setup. We use 2 sodium iodide detectors, and these detectors are placed close to the cell, as you can see, carbon anode and the cathode. The whole setup is placed inside a lead enclosure in order to reduce the background. So let's see the results. So this is a very complex table. I'll just summarize it. You can see here, we could not find any significant photons. However, we observed transmutations. So again, the correlation was inconclusive. We also tried to look for photons with the high purity germanium detectors, and but still we were unable to get the photons. However, we got some signals from up to 100 keV, but again, they were spurious counts because we didn't do the shielding well. So again, shielding is very much important in looking for photon or particle signals, especially when we are working at high voltages. Because when we work at high voltages, we have a glow discharge in our systems. And that can actually, the electromagnetic signals from that can actually interfere with any metallic component. That has to be properly grounded and shielded. So again, then we decided to look, and since we got the spurious counts, we decided to take help of X-ray sheets. And so what we did was we chose dental X-rays. So these are basically the dental X-rays that the dentists use. We placed 3 dental X-rays one over another. And then this white part that you see is basically a lead block. So what we tried to do is that we put the lead block so that if the photons are passing into the page, in this one, The portion below the lead is not going to be reacted, whereas the portion which is not being covered by the lead is going to be reacted. So this is our cell. We're using H cell, just trying to separate the catalyte and anolyte part here. So we put these detector near to this cell, and what we found was this. So assume this is our cathode. S1 dental X-ray is closest to nickel, S2 is farther, and S3 is farthest. So you can see the effect of this lead block. You can see here the center portion, which is the white, which is actually white in color, is not reacted, whereas this black is a reacted part. And this reaction faints as we move farther from this nickel cathode. For example, in S2, you can see it has gone faint, and in S3, it has gone fainter. So basically, the photons is traveling from S1 to S3. Could this blackness or reaction that we observed in these dental X-ray signals that we have a photon emission? Well, we are still inconclusive because since we worked at higher voltages, the temperature of the liquid was high. And we did a control experiment where we put half of the dental X-ray in a hot water, and then we found that this actually responds to hot water. So this is still inconclusive. OK, so now I move on to the main focus of my PPT today. This is the recent work that has been done by us. So we, along with photon, after photon, we are trying to look for particle emissions using CR39. So in the figure here, you can see a transparent chip. This is basically a thermoset polymer. And it's Columbia resin 39. And it's basically used to track particles, typically used in space science applications, and also also used as dosimeters in many places. So what we see here is a carbon anode and a cathode, which is wound over CR39. You can see the typical dimension is mentioned here. What we do is we put this setup inside a D2O solution containing 1 millimolar of palladium chloride and 10 millimolar of lithium chloride. The solution color is brown. We run the setup for like 3 days with 5 to 50 microampere current range. And after 3 days, what we find is that the color fades. At the point when the color fades, we apply magnetic field directed from cathode to anode. The magnetic field value is about 2500, 2700 DOS. And then we actually run this setup for 100 milliamperes for 4 days. And after that, we remove the chip, and then we etch it. So it's a typical procedure in order to visualize the tracks which have been generated by the source in the CR39. So basically, it's a 6 molar NaOH solution, and the etching is done at 80 degrees Celsius. It typically removes like 1.2 to 1.5 micrometer layers per hour. This temperature would do that. And so what happens during the etching is that the particle, which when travels through the CR39, breaks the molecule of the polymer. And those latent tracks are basically preferentially etched as compared to the bulk region of the CR39, where the particle has not basically interacted. So the speed of the particle track etching is greater than that of the bulk. So what we get is a particle track. And this can be seen easily using an optical microscope. So let's have a look at what we got. So we basically used platinum cathode in heavy water. And so this is figure A is a typical image of an unexposed and etched CR39. So the typical surface roughness is 1 nanometer. We use optical profilometer to measure. And then figure B is the image of CR39, which was placed along the platinum cathode throughout the experiment. What we see here are circular and elliptical particle tracks, and the diameter varies from 3 to 45 microns. We also did depth profilometry. Again, we see the tracks, and we measured the typical depth range of 1 to 15 microns. Now, another interesting thing to note is that we observe the tracks spread all over the CR39 area, not only near to the platinum cathode, but actually all over the CR39 area. And so now the task is to try to find out what could be the nature of the particle. So here we'd like to discuss first the standard reaction of a carbon with a neutron. So neutron hitting a carbon can undergo multiple reactions. And so the one which is important for us here is the last one, a neutron hitting a carbon and splitting it into 3 alpha particles. The threshold for this is like 9.6 MeV. It's quite high. And the signature of such reactions can be observed on CR39, and the experiments have been already done. There are lots of references. I have mentioned 2 of them. And this is what we observed in our experiment. So this is basically the signature of this reaction, high energy neutron breaking carbon into 3 alpha particles. There are many more decay pathways which are shown here. And so we can have double tracks also. We can have double tracks which are apparently triple track. And so we have a variety of tracks. So, but the important message which I wanted to convey through this slide is that there is a presence of high energy neutron in the experiment. And the threshold is 9.6 MeV. So, and then another important observation from our group, saturated tracks on rear side of exposed CR39. I'll go slow with this slide. So this is our CR39. Let's say this is our CR39, and we have a platinum cathode here. On the A phase, is basically at the A phase, and the B phase is the rear side of the CR39. The width of the CR39 is 1.5 mm, and the length and all these things are in centimeters. So basically the particle, if it is emitted from the cathode, is basically entering from the A phase and going towards the B phase. So at the front phase, what we have was, this is a lot of particle tracks. It's all congested particle tracks. So we have a high density of particle tracks. But on the rear side, what we observed was saturated particle tracks. I'd like to again mention that the width of this CR39 is 1.5 mm. If this particle would have been a charged particle, so we can do a stream calculation and we can find out, let's say a 5 MeV proton would not even travel 1 mm in this medium, CR39 medium. So since these are solitary tracks, the single tracks, the tracks on the front surface could be because of protons, because they do not need that much energy. They can deposit their energy on the front surface, but it would be difficult for them to travel throughout 1.5 mm width of CR39 and create tracks on the rear surface. And why do we say that we have a neutron fluence in these experiments is that this is a typical signature of neutron fluence in CR39 beam experiments. This is the reference which I have taken, and such observation, again, I'll just read it again. Such observation is typically observed in fast neutron spectrometry in CR39. The reason why we have saturated tracks on the backhand side, the rear side of the CR39 is that the particle moves from, the neutron moves from the front face to the rear face. It loses its energy, and which basically simultaneously increasing its collision probability. And so we have lots of reaction of neutrons with the hydrogen present in CR39. So CR39, it's got carbon, hydrogen, and oxygen. So this is our argument why we feel that we have a neutron fluence in our experiments. Next, what I did was I measured the diameters of solitary tracks and tried to plot a histogram. So we have a typical histogram. So we can see the track. I'm sorry, the numbers are quite small. The track diameters are in micrometer, and it starts from 3.5 micron, goes up to 21 microns. And I seem to have maximum frequency from 10 to 13 microns. So we couldn't actually, so in order to pull out the values of energy, yes, okay, thanks. So in order to pull out the energies from these measured track diameters, we use the published track diameter versus energy data of protons. So this yellow curve is for a 6-hour H. And we used the same CR39, which this group has used. We also kept the parameters same, the etching parameters similar to what they have done. And what we got was that assuming that it's all proton on the surface, the energy ranges from like 9 to 1 MeV. So basically, it's 0.9 to 9 MeV. So now, if the energy of protons is like 0.9 to 9 MeV, then we are sure that the energy of neutrons is higher than that, because the neutron is basically colliding to the proton and then kicking it so that the protons are creating tracks in CR39. So with the same cathode, we also did some transmutation studies. So we did some wavelength dispersive spectroscopy, and what we found was, we found 3 elements: nickel, silver, and gold. We reject nickel because when we did the ICP-MS of the cathode, reacted cathode, we found out that the palladium chloride salt that we procured from Sigma Ulrich already had a bit of nickel. So we are not considering this as a transmutation product. However, silver and gold were not present in ICP-MS. So we are sure that these are transmutation products which were seen through WDS. We also did some ICP-MS to know the isotopic shifts, whether they are available in our cathodes or not after the reaction. So here we can see the palladium, which was coated on the platinum cathode during the electrolysis. So basically, we dissolved that. And if you look at the 106 to 104 palladium ratio, unfortunately, we still don't know the reason why we couldn't measure even the natural value of this ratio. It was kind of absurd, but we were able to measure the natural values of other isotopes. And in 106 to 104, you can see there is a shift from 7.59 to 7.17. So basically, the ratio has gone down. But we cannot believe this result because it is not matching the natural values. So that's it. That was my presentation. I will just take a minute to give a summary. So we found elemental transmutation while light water glow electrochemistry did not provide gamma signals. Palladium deuterium codeposition displays transmutation and particle tracks in CR39. We want to do a controlled light heavy water experiments, basically mixing these controlled amounts of heavy water, and then to look for the particle tracks and transmutations. And we need more and more better and better material and electrochemical characterization techniques to study our cathodes after reaction. And at last, interpretation via models and mechanisms, which we have started this month. And hopefully, we're trying to do something. We'll try to come up with something. And thanks. And we'd like to have questions, comments, suggestions from you. Any feedback would be appreciated, because we are going to write a paper, and it would be better if, just open up and shoot the bullets.
Okay, thank you very much. Thank you for the talk. So now we are open for questions. Are there any questions? Oh, the back somewhere. Okay.
Yeah. Thank you very much for a very interesting presentation. I have a question on the transmutation experiment. First one.
Okay.
How long, usually, typical experimental time? Usually, you electrolyze just 1 hour or something like that?
So we started with longer hour experiments. Mm-hmm. Like we started with 12 hours, we went to 24 hours. But then we wanted to, then we wanted to know the exact voltage. We went on reducing the voltage in order
Voltage,
to, yeah,
okay.
in order to look at what voltage transmutation starts. So we're looking for that transition point. We couldn't find it. So that, and then what we did was we went on reducing the time also. And with alloys, what we found was we could generate transmutations like in 1 hour. I mean, we have seen it with 30 minutes also.
Okay, thank you. Thank you very much.
So another question?
Hi.
Morning. Thank you for the.
Can I ask the question?
Okay, yeah, please go on.
Anatoly Klimov, I have one question for you. The first one.
Please go
You
on.
change the current from the 50 microns microamperes to the 4 amperes. What changes your experimental results dependent on the current value?
Okay, so I'd like to repeat the protocol. What we did was we run the cell at microamperes current for the first 3 days, and then we increase the current to milliamperes, not amperes. We just increase the current. So the reason to run the electrolysis at lower currents was to ensure that we have a uniform loading. So that's why we work at lower currents, and then we increase the current so that D2 evolution can happen, and then after 7 days, we just look for the transmutations. So the microampere currents, it's simply we just want to have a uniform adherence of deuterium. That's the reason. Because we worked at higher currents also, but I did a lot of literature review of Pam Boss's work, and this particular work is basically inspired from her. And we kind of wanted to replicate her work, and we were quite successful in this.
Thank you.
Okay, go ahead.
Yes, please.
I'm reporting something
The microphone? Okay.
Yes. You suggested to change the mic.
Yeah. Okay. I'm reporting something that another group doing this claims, let's say. So it's not me, but I report something that a group has found. They say that the track or part of the tracks can be coming from recombination of oxygen and hydrogen on the electrode, radicals making the traces.
Okay.
So since
Okay.
you say in order to avoid future things,
I understood you.
ways of ensuring that this part is filtered, so to say, probably would be...
Yes, so I would like to put up a comment. What we did was we displaced the CR39 2 centimeters away from the cathode. That can also be done, and still you will have tracks. The second thing is, one of our collaborators, he did some experiment at BARC, Bhabha Atomic Research Center. That's the premier institute of atomic research center in India. They also repeated the same thing, same experiment was repeated at the same time. They got the same results. They all, we didn't had proper nuclear detectors. That's the problem with us, but we couldn't just sit idle. So they use helium-3 detectors, they use CR39, they use epoxy resin, they use diamond detectors, and they found signals of neutrons. Okay. So that's my response.
Okay, I think Mathieu Varat wants to ask a question.
Yes, just to add up to your upcoming publication eventually, there's a long tradition of talking in current density in electrolysis.
I agree.
Yeah, I advise you to use that
Correct,
because
correct.
it's like a national,
Yes, yes.
international
That's right.
metric of
That's right.
how much stuff
Yes,
is happening.
yes.
I did my master's thesis on electrolysis of palladium with carbon anodes.
Okay, great.
Yeah. And I was doing SIMS measurements of the
Okay.
surface, so you may have a look at that.
Sure.
It happens that the carbon anodes are quite dirty. So I wouldn't be surprised that the oxygenation of your carbon anodes and then the attraction of the cathode during the electrolysis process might be one of the reasons why you get some of the new elements that you claim are coming
Okay,
from something.
so-
It might actually be
Yeah,
coming
sure.
from your anode.
That's
as
correct.
simple as that.
Okay.
So my comments on that, the first thing that we ensure, actually we have been using metal anodes earlier. And we have been discussing a lot, and then we switched over to carbon anodes. We make sure that the carbon anodes that we procure are from the best of the best place. The second thing is we do not rely on the MSDS or data sheets of companies. We try to do our own ICP-MS and all kind of spectroscopy. The second argument why this is not impurity is that, again, if it would have been an impurity, the isotopic shifts towards natural values.
Absolutely.
The second point is that sometimes we do not see transmutations. If it would have been an impurity which is coming from the carbon anode, traveling through the electrolyte, getting deposited in the cathode, and then in all the cases, in all the runs, we would have seen the transmutations.
Okay,
Those
I
are
think
my
we have
comments.
I think we have to. Last question. Who's? We're too many.
Maybe.
Francesco, you are out of the game. You know.
Hello,
I'm very
Prof.
skeptical about transmutation, of course, because it can be something completely different. It can be selective diffusion, and we know this kind of things that some isotopes are going to the surface, some going to the bulk, and you can change everything, okay?
Yes.
So if you measure only surface, you cannot say anything about
Yes.
transmutation or something like this. My point was different. Have you measured the heat excess?
We actually, I was the first student who started ELIANA experiments, so we kept our focus on nuclear transmutations only. And so we actually have not, we are trying to look at the setups and learn from that so that we can create our own setup in our own lab. So we are looking forward to that. And another thing, your first comment, we did some measurements, we did some depth analysis using SIMS. The transmutation elements, of course, it could be diffusion, but like as for example, electromagnetation would require higher voltages. We do the experiments for 10 hours at lower voltages and lower currents.
No, it depends on temperature, for instance. It was
Yes.
my second question, if you could measure temperature as well, you know, not only heat excess, but that's temperature. It is very simple to do it, you know, and then you can see something probably.
Well, I think we have to stop now because the coffee break will
Thanks
be
for
removed,
comments.
you know. We will not have any coffee after that. And as you're all sleeping, thank you again, Mr. Kumar.